We have 7 types of electromagnetic radiation. They're all produced, every single one of them is produced in general by what? Yep. I'm sorry? Okay, every single one of them consists of the same thing, an electric field wave, a changing electric field, and a changing magnetic field. But what fundamentally causes that changing electric field and that changing magnetic field? Travis, you're right. Okay, in the end, to move that wave from one place to another, we need a changing electric field and we need a changing magnetic field. But what causes that changing electric and magnetic field? Good, accelerating electric charges. Okay, if I just write down electric charges, an electric charge, we know that that will produce what kind of field? Okay, just an electric charge that's at rest. It's going to produce an electric field. And, sorry, Tanner? It's also going to produce a gravitational field. Is it going to produce a magnetic field? No, then it's not going to produce electromagnetic radiation if we have a charged particle at rest, right? You got to have an electric field and a magnetic field. Okay, this produces the electric field in gravity because it's got mass, but that's it, end of story. If we have an electric charge that's moving at a constant speed, then what's it going to produce? It's going to produce an electric field still? Sure it is. If it's at rest and it produces an electric field, then it's going to produce one if it's moving as well. What about a gravitational field? Does it produce a gravitational field? Has it got mass? Yeah. Produces a gravitational field. Does it produce a magnetic field? Right? Yes, it produces a magnetic field. Good. So then that must produce electromagnetic radiation, right? Because all you need for electromagnetic radiation is an electric field and a magnetic field, right? No, Travis said just a minute ago, we need a changing electric field and a changing magnetic field. And an electric charge moving at a constant speed produces a constant electric and magnetic field, not a changing one. So how do we get the changing electric and magnetic field, the electromagnetic radiation? Okay, somebody said it, I think it was Max said it just a minute ago. We have an accelerating charged particle, speeding up, slowing down. That produces a changing electric field, constant gravitational field, and a changing magnetic field. That's what produces the electromagnetic radiation. Because, as Travis was alluding to when I asked the question in the first place, you need a changing electric field to cause the magnetic field. And you need a changing magnetic field to cause the electric field. And that's how the whole thing ends up being propagated. The whole thing ends up being moved, right? Is by having that changing electric field causing the changing magnetic field, which in turn causes an electric field, and so on and so on and so on. Make sense? What's the big word? What's the big word that we think of oftentimes when we associate electricity with magnetism, especially in electromagnetic radiation, when we associate the electric field with the magnetic field? It's the P word, perpendicular, right? The electric field is always perpendicular to the magnetic field. One of them's on the y-axis, one of them's on the x-axis. One of them's on the z-axis, one of them's on the y-axis. It doesn't matter. It doesn't matter which one is which. It doesn't matter which axes we're dealing with, as long as they're perpendicular to each other. What do we know about the motion of this wave as well? If here's my electric field, here's my electric field's on the y-axis here, okay, with my hand. My magnetic field is on the x-axis here. Which way is the wave going to move? Sorry? Okay, so the shape of it is a sine wave. It's a sinusoidal wave, right? Okay, but which way is that sinusoidal wave going to go? Sorry? On the z-axis, right? It's either going to go towards you guys or towards the front of the room. We don't know which way on the z-axis it's going to go, but we know it's going to be perpendicular to both the x and the y-axis, which means it has to be on the z-axis, right? One way or the other, right? All right, we talked about 4 properties of waves that are exhibited by electromagnetic radiation that support the wave theory of EMR. Okay, what were those 4 properties? Think back to physics 20, where we learned 3 of them. Polarization, yeah, that's the one that we didn't learn in physics 20. Polarization. Polarization is that filtering out of components of a wave. So we've got waves going in every which direction. Here's a wave like this. Here's a wave like this. Here's one like this. Okay, all going in different directions. Polarization is filtering out all but one component, all but this, or all but this, or all but this. Okay, it's filtering out everything but one. That's polarization. And since that's a wave property and electromagnetic radiation undergoes polarization, then there's evidence to support the wave theory of light. What's another one? What is it? Diffraction. Diffraction is the spreading out of light around a barrier or through an opening. Diffraction. It's another one. Kind of goes with diffraction sometimes. What were you going to say? Refraction. Okay, that's not the one that I was thinking of. That doesn't really go with diffraction, but it's correct. Refraction is the bending of a wave. Diffraction, the spreading out of a wave. Refraction, the bending of a wave as it goes from one medium to the other. Both of those are properties of waves, and both of those properties are exhibited by electromagnetic radiation. Therefore, wave theory of EMR. Yep. Yes. The one that goes with diffraction is interference. Sometimes. It doesn't always go with diffraction, but sometimes it does. Interference is when two waves come together, right? Sometimes we form a bigger wave, sometimes we form a smaller wave, constructive and destructive interference. Since light, or EMR, undergoes interference, then again, more evidence to support the wave theory of light. All right, I'm not going to press the button right now because the next slide is going to show us the 7 types of EMR in order from smallest frequency to highest frequency. I want you to give me those 7 in order, before I press that button on the slide. Radio waves, good. What's next? Microwaves, good. What's next? Infrared radiation, good. What's next? Visible light, what's next? Ultraviolet, good. X-rays, gamma rays, good, good. All right? You guys think you're so smart? Or is it rhetorical? Rank them in terms of increasing wavelength. Gamma rays. Gamma rays starts as number 1, right? Increasing wavelength, we start with gamma rays because that's the one with the smallest wavelength, right? What's next? X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Good. It's harder to go backwards, isn't it? You know what? It's like saying the alphabet backwards. It's really hard. Okay. These are the 7 types of EMR in terms of increasing frequency, in terms of increasing energy, in terms of decreasing wavelength. Okay, if we're asked a question to rank them in terms of increasing frequency, hey, then we just remember that song, right? And we're gonna get that. Okay, guaranteed we're gonna get that right. If we're asked to rank them in terms of increasing wavelength, what I would do, hey, and this is still, you know, even after however many years, this is still what I would do if I got a question like that. I would write this down. I would literally on my paper, okay, on my test or on my scrap paper or whatever, I would write them down in this order because that's the way I remember them, is that order. And then what would I do? I just read them backwards. Okay, I don't want to think of them backwards. I want to read them backwards. I want to think of them going forwards like this, radio waves, microwaves, and so on. And I want to just read them backwards if I have to. Okay, there's less chance of making a mistake if we write them down and read them, gamma rays, X-rays, ultraviolet, and so on. All right, let's refresh our memory here as to how each of these types are produced. Radio waves and microwaves were all produced by what? Oscillating electric charge. What does oscillating mean? What does oscillating mean? Yeah, going back and forth, back and forth. AC current, alternating current in our houses goes back and forth at 60 hertz, 60 cycles per second. That generates radio waves, weak radio waves, very weak radio waves, but still radio waves are generated right now in this room as the electrons go back and forth at 60 cycles per second through the wire. Radio waves are frequency 60 hertz. Infrared, visible light, ultraviolet are all produced by Go ahead. Yeah, electron transitions. You guys have learned a little bit about this in chemistry class, probably. Electrons can make a transition from the first level to the fourth level. That doesn't give off EMR. When it makes a transition from 1 to 4, it absorbs EMR. It has to absorb energy to jump a level. But when it falls from level 3 to level 2, or level 5 to level 3, or level 4 to level 1, or whatever, it gives off EMR. Okay, one type or another. Infrared, visible light, ultraviolet, or occasionally an X-ray. We don't usually put that in the same class because that would require a really big, a really energetic transition to produce an X-ray. Usually X-rays aren't produced that way. Sorry, we shouldn't have lumped these two together. X-rays and gamma rays are separate from one another. X-rays are produced by? Yeah, rapid deceleration of electrons. We got to get them going really, really fast, like really fast. 10 to the 6 meters per second, right? Hundreds of thousands of meters per second or millions of meters per second. And then we smash them into a target and we stop them almost instantly. Okay, the kinetic energy of the electron has to go somewhere. It gets transformed into light energy, to electromagnetic energy. Okay, it gets transformed into an X-ray. So we're going to say here, rapidly decelerating electrons. And finally, gamma rays are produced by nuclear decay, radioactive decay. Okay, in the process of nuclear decay, matter, right, mass, is converted to energy. We talked a little bit about this yesterday. I think it was Travis that asked the question, well, doesn't the total amount of energy remain the same, or doesn't the total amount of mass remain the same? Was that you, Travis, that asked the question? The answer is no, it doesn't, right? The total amount of energy doesn't remain the same. The total amount of energy / mass remains the same. But we can convert energy to mass and mass to energy. Right? We can produce energy. We can create energy, kind of. But it has to come from something still. It has to come from matter. We can create matter or destroy matter, but it has to come from energy, if that's the case. All right, finally, last part of our review here. We have to remember 21 different ranges here with these 7 types of EMR. We have to remember the 7 different frequency ranges, the 7 different energy ranges, the 7 different wavelength ranges. But there's a shortcut. That's the good news. There's a shortcut, a big-time shortcut, where we only have to actually memorize 3 things. The frequency ranges of 3 of these types of EMR, and then we'll figure out the rest. We'll calculate the rest. Which frequency ranges are we going to remember here? Which are the ones that I want to memorize? Microwaves, visible light, X-rays. We remember those 3 things, we should be good to go. What's the frequency range of microwaves? 10 to the 9 to 10 to the 12 hertz. I don't know about you, but even a number like that, that's hard for me to remember. I hate remembering numbers like that. I'm terrible at it. Okay, I remember it because I've done it a million times before. Okay, if I was in grade 12, right now, going through this for the first time, you know what, you answered that question, I probably wouldn't have answered it. I probably would have missed it because I'm terrible at remembering things like that. Okay? That's something that if you're like me and bad at remembering things like that, then you got to work hard at that. Okay, you got to remember that because sometimes it's asked, sometimes it's not, but we got to be ready for it, just in case. 10 to the 9 to 10 to the 12 hertz. Visible light, this one's even harder. The good news is the exponent's the same, but we have to remember a base for visible light. We have to be specific for this one. Down? Right? Good. 4 times 10 to the 14 is 7.5 times 10 to the 14 hertz. Good. And then, of course, the last one is X-rays, which is, this is the one that I always, for whatever reason, get mixed up if I get one mixed up. 10 to the, yeah, sometimes I like to make it 10 to the 17 to 10 to the 19. And I'm not sure why I do that sometimes. But that's right. 10 to the 17 to 10 to the 20 hertz is correct. So if I give you a type of EMR, it's a mysterious type of EMR. You can't see it, not visible light. It has a frequency of 6.5 times 10 to the 4 hertz. What kind of EMR is it? Radio waves. I give you one that has a frequency of 9.3 times 10 to the 18 hertz. What is it? X-rays. I give you one that has 5.5 times 10 to the 23 hertz. What is it? Good. What if I give you one that is, let's make it 3.0 times 10 to the negative 7 wavelength. 3.0 times 10 to the negative 7 meters. What's that one? Oh boy. Let's figure it out. Let's figure it out. Okay, we don't know that it's radio waves because it's 10 to the minus 7 meters. That's a wavelength, not a frequency, right? We got to get a frequency from this. So let's use the wave equation that we learned in physics 20. F is equal to V over lambda. V is 3 times 10 to the 8, right? Lambda is 3 times 10 to the negative 7. What do we get there? 3 divided by 3 is 1 times 10 to the 15. 1 times 10 to the 15 hertz. What's that going to be? That's going to be ultraviolet, right? So listen, we didn't even memorize the frequency of ultraviolet, let alone the wavelength of ultraviolet, but we were still able to determine what this type of EMR was based on the wavelength by converting it to frequency and then essentially comparing it with the frequency of visible light and X-rays, finding that it was in between. Make sense? Hey, I would say that probably about half the time, or maybe slightly less, but about half the time, you have to be able to identify a type of EMR based on its wavelength or its frequency or its energy, which we're going to learn later in the unit how to do that one, okay? About half the time. Is it worth reviewing this stuff? Is it worth studying 3 different frequency ranges? Yeah, I think it probably is. If you had to memorize all 21 of these things, you know what I might say? I might say, you know what? I might take my chances on it. But 3 of them, okay, I think we can do that. 10 to the 9 to 10 to the 12, 10 to the 14, and 10 to the 17 to 10 to the 20. All right? Okay. Let's move on a little bit here. I want to show you a little experiment right now that was performed by a guy named Heinrich Hertz, who's the guy that has the unit for frequency named after him. It's not a coincidence, by the way. The electromagnetic radiation has a frequency because it's a wave. He was the first guy to experimentally detect electromagnetic radiation. When you do something like that, you get a unit named after you. Hertz performed an experiment with what we call a spark gap apparatus. A spark gap apparatus consists of a transformer. A transformer is simply a device that changes a small voltage into a big voltage, or a small potential difference into a big potential difference. So maybe you got 10 volts over here, maybe you got 1,000 volts over on the other side. We're not going to concern ourselves exactly with how that happens. Okay, that's not the point of this. Okay, a transformer can change a small voltage into a big voltage. That's how it happens right here. Okay, this is the process where it happens. Forget about how it happens. That's where it happens. We got a small V over here. We got a big V over here. The reason we want a big V, the reason we want a big voltage or a big potential difference is because we want electrons to jump across this little gap here. It's kind of like the gap in a spark plug. Right? How many people have literally held a spark plug in your hand? There's a little gap, okay? It's a very, very small gap in that spark plug. There is a big potential difference in your car. Okay? It's only a 12-volt battery, but in the end, we get 12 volts stepped up to a bigger potential difference, which allows the electrons to jump across that gap. And in your spark plug, it burns the fuel, right? That's the purpose of it. It ignites the fuel. It's almost the same thing here, except we don't have gasoline to be ignited here. We get a big potential difference here. That causes electrons to jump across this little gap, like the gap we have in a spark plug. Now, if Maxwell's theory is correct, then that should produce electromagnetic radiation, right? Because if you have electrons just sitting here on one side of the gap, and then they jump to the other side of the gap, they had to accelerate to do that. If Maxwell's theory is correct, then this should produce electromagnetic radiation. Accelerating charged particles should produce EMR. So Hertz puts up an antenna to detect the EMR. How does the antenna detect the EMR? Well, if you have a changing electric field and a changing magnetic field, what's it going to do to this conductor, this metal antenna? What's going to happen to it? Yeah, not quite, but you're pretty close there. Yeah, it's going to generate an electric current. There's going to be an electric current going through this antenna, a small one, but still an electric current going through the antenna. That's how antennas work. Changing electric field and magnetic fields generate electric current in the antenna. That's how every antenna works. That electric current goes into your radio or whatever it is, and then it gets converted to a sound or gets converted to, a video signal or whatever the case may be. So we accelerate electrons across this gap with a really big potential difference. If we detect an electric current in this antenna, then Maxwell's theory must be correct. Think about that. If we detect an electric current in this antenna, then that accelerating electric charge must have produced EMR, and that EMR must consist of a changing electric and magnetic field. Otherwise, we never would have got that current in the antenna. So what happens here? Flip on the switch, lo and behold, we get a current detected in the antenna. Maxwell's theory has been proven correct, or at least been supported. Evidence to support Maxwell's theory that A, accelerating charged particles generate EMR, and B, that EMR consists of a changing electric and a changing magnetic field. He was the first to experimentally detect electromagnetic radiation. He detected it, he saw it, there was a current produced in the antenna. He called the waves, the electromagnetic radiation that he used, that he produced here and detected in the antenna, he called it radio waves. Why did he use radio waves? Well, he didn't exactly. He didn't know what he was using, right? He didn't say, oh, I'm going to use radio waves, because radio waves weren't there, right? Nobody had called it radio waves or anything before that. He just generated some type of EMR. And the type that he caused, the type that he produced, he named them radio waves. They just happened to be radio waves, these really, really low frequency waves, because quite honestly, that's the easiest type to produce. It's a lot easier to produce radio waves with moving a charge back and forth, say with an AC power supply, than it is to produce gamma rays by splitting the nucleus, or to produce X-rays by smacking a really fast-moving electron into a target. They're easy to make. We make them all the time. As soon as you flip on a switch, as soon as you turn on the switch to any electronic device, you're generating an incredibly low intensity radio wave, because you accelerate electrons when you flip on that switch. Okay, you make radio waves. All right, everyone, we're going to take a look at a few questions here right now. I'm going to give you a chance to work on those for about 10 minutes. Check and reflect page 647. The questions that I want you to work on are 1 and 2, 5, and 7 to 14. So you're probably not going to finish those up in the next 10 minutes, but I'll give you a good chance to get a start on them at least, okay?